Very good morning, students. Today we are going to discuss about phasor diagram of transformer on no load. So for that we have to understand first the parameters involved in the phasor diagram. Uh, Generally we know that we are having two windings in a transformer, correct? One is primary winding, another one is secondary winding. Usually the primary winding is connected to the source and secondary winding is connected to the load, and the supply voltage or source voltage is V1 and current flowing to the primary winding is taken as I1, and EMF induced in the primary winding is taken as E1, and the flux links through the secondary winding through this core, correct, and EMF induced in the core due to the alternating flux is E2. In this case, in no load, no, E2 is equal to V2. V2 is nothing but terminal voltage of the secondary winding. Here there is no load, so terminal voltage and the induced EMF both are same for under no load condition. Okay, and the secondary current I2 is equal to 0 because there is no load. Okay, so these are the basic parameters we must understand, and the equivalent circuit is necessary to understand the parameters involved in the no load furthermore, correct. And this is the primary winding impedance, which includes resistance and reactance of the primary winding and resistance and reactance of the secondary winding here. And to represent the core loss and magnetizing current, no, we are using a shunt component. This resistive component is responsible for the core loss. It can be represented IW or IC. See here, I have given here IW or IC, working component or core loss component. And similarly, no, the magnetizing component is represented by the variable I mu or IM. It can be represented in both variables. And while we draw the phasor diagram, we have to take the reference as magnetizing current. I have taken reference, correct. So the magnetizing current and flux will be in phase. Why? Because the current is responsible for the flux. So flux and current are always, not only here, every time the both are in phase, correct. And the magnetizing component is represented by the pure reactance, correct. So the voltage, the input voltage leads, or in another words I can say the magnetizing current lags the source voltage by an angle 90 degree, correct, because this is the exactly 90 degree due to the pure reactive component, correct. Now V1 is represented with this straight line, correct, and then working component, the or core loss component, is represented by resistance. We know in resistive circuit voltage and current are in phase, hence IW and V1 are in phase, correct. So I have drawn magnetizing component and the working component. Now we know from this diagram, no, equivalent circuit, vector addition of IW and I mu is I naught, correct, because I naught is split into two parts, IW and I mu. So we have to draw a vector addition. Okay, so with the help of the parallelogram here we are having right angle triangle, so no need to go for parallelogram and all. So how we get, no, see here, the component parallel to IM I am drawing, and the component parallel to the IW I am drawing, and the line which is a diagonal or connecting these two is nothing but vector addition of these two. So this line is I naught, correct, and the angle between these two is usually represented by phi naught. Okay, power factor angle, no load power factor angle. And one more left out is E2 and E1. Induced EMF in the primary and secondary winding are just opposite to the supply voltage. Why? Because we know by Lenz's law E is equal to minus N into d phi by dt, correct, minus N into d phi by dt. So induced EMF opposes the cos, correct? That's what we are having minus. So we know for minus 1 the equivalent angle is j square, correct? J square is equal to minus 1. J contributes 90 degrees, so j square is nothing but 180 degree. That's what the induced EMF is, 180 degree opposite. See, this E2 and E1 are 180 degree displacement with the source voltage, or just opposite line with the source voltage, correct? Now the same diagram I show here for your understanding. See, this one is phi naught, IC or IW, IM or I mu. Please understand, both are same only, okay? I mu or IM. Now my aim is to find out the value of IC and IM in terms of I naught. Okay, it looks like a square, no? The same, the length here, no? The same length will be here. So I can say the length of the opposite side is IM, adjacent side is IC. So it looks like a right angle triangle like this. With the help of the Pythagoras theorem, I can derive this one. So this is your phi naught, okay? This is your phi naught, and this is your adjacent side, this is your opposite side, this is your hypotenuse, correct? So for cos phi naught, what is cos phi naught? Adjacent by hypotenuse, okay? Sin phi naught is opposite by hypotenuse. So based on that, I can derive these two things. Im is equal to, see, Im is opposite side, no? So what you will get? I naught sin phi naught, and then IC is equal to is adjacent side, correct? So IC is equal to I naught cos phi naught. With the help of this Pythagoras theorem, again I naught can be calculated like this formula also, square root of Im square plus IC square, because I naught is the vector addition of IC and Im. Okay, this is very important phasor diagram. If you understand this, we can draw voltage regulation as well as load phasor diagram for transformer on load also. Thank you for watching this.